Welcome to Syzygy, Episode 6, 14 Galaxy Pile-Up Causes Cosmic Chaos. Welcome back to another episode of Syzygy, everyone's favourite astronomical podcast, recorded here in the sunny University of York campus here in the UK. Today we're going to be talking about something really, really big and really, really far away. Astronomers have found an enormous cluster of galaxies in a very, very small space on the far-flung regions of the universe, and that's challenging what we think we understand about evolution out there in the universe. It's been a really interesting problem. Joining me on the microphone, as ever, Dr Emily Brunsden.
Hello.
So, Emily, before we get into all of this big galactic pile-up stuff, we've had a listener question.
Yes,
very exciting. Very exciting.
Yeah, so this is a question from Steve from York.
Hey, Steve.
Hey. He's asking a question related to our very first episode, which was about finding these rogue planets through microlensing, and these planets were in a galaxy that was incredibly far away.
That's right, all the way back to episode 1.
Yeah.
Gosh, so long ago.
So Steve asks, basically, can we learn a bit more about or tell us a bit more about the rogue planets in our galaxy? So he says, has anyone tried to make a model of the Milky Way and calculate how many rogue planets there should be? Or are we just a bit too close to see those kind of things happening?
Oh, okay. Interesting question. So back in that first episode, we talked about a whole bunch of rogue planets, but they were in a completely different galaxy, and they were found by very clever means. And if you want to know more about that, go back and listen to episode 1 if you haven't yet. But have astronomers done models of our galaxy? I'm guessing the answer is probably yes.
Yeah.
Because it's our galaxy and it's right here and we can do that.
It's home. Yeah. So actually the first thing that we knew about rogue planets, we detected them in our galaxy first.
Right.
So these are these planets that don't have a host star. And pretty much the only way we can detect them is if they happen to pass in front of something else that's bright, and they do this microlensing event where you get the sudden increase in brightness of that background object.
And that's a fairly random thing because, again, these are rogue planets. They're not orbiting. So you're not looking for something that, there's a blip in front of that star and then there it is again and then there is it again. There's no repeating here. It just happens to wander in the path.
Yeah, and it has to be a really precise alignment for it to happen. So it's also very rare.
Mm-hmm. Then again, if there are lots of them, it might be happening all the time. So...
yeah, so we look at huge patches of the night sky that have lots of stars in it. So this is the plane of the Milky Way through the sky and basically towards the center of the Milky Way. We have the most stars, so you're going to find the most microlensing events. And so far we have on the order of about 20 good planets that we've found in our galaxy using this technique. And then what we can do with that information is, much like we did with Kepler, we saw a few thousand planets going around other stars, and therefore we can say, well, roughly every star in the galaxy has a planet. We can do the same thing and say, well, maybe 1 in 4 stars, for every 4 stars, there's one of these rogue planets floating around in our galaxy.
So that's still a lot of rogue planets.
Yeah, it's quite a few.
Yeah.
Quite a few. They're either these failed stars or they might have been kicked out of their original solar systems when they were formed. So we don't really have a precise map of where all these things exactly are, but we can say they're roughly this many of them, at least in the local galaxy that we can see.
And does that tend to fit with what we've seen in other galaxies as well? I mean, going back to our first episode and the enormous numbers of planets that were seen, rogue planets that were seen in that galaxy. Do those models tend to agree, or is it still pretty early days in trying to figure this stuff out?
It's very early days, but actually when you add up the amount of mass in a galaxy, you've got a big enough wiggle room with how many planets you add into that it still works, basically.
Cool. Well, always good to get a listener question. If you've got a listener question, listeners out there in listener land, then you can contact us at the Syzygy website, syzygy.fm, that's syzygy.fm, or on Twitter. Go and find us, SyzygyPod, at SyzygyPod, and send us your question, and we will include it in a future episode if we can come up with a decent answer. Even if we can't, we'll make something up. So send us your questions. Now, on to today's topic. This paper that was released about a month or so ago in Nature which is about the discovery of a very large cluster of galaxies quite a long way away. Emily, talk to us about this. What's going on?
So we have got 14 galaxies, which are all piling up, and they're piling up in a very, very small space.
Now, just to be clear, this is not something that we need to worry about. This is not sort of looming overhead. Oh my God, here come the galaxies. This is not that kind of pileup. This is a very long way away.
Yeah.
It was actually detected as a really tiny dot in the sky. And when you zoom in and look at it really closely, it resolves into 14 galaxies. All
yeah,
together.
we're not going to get caught in this pileup
No.
anytime soon.
No. This is not a problem for us. It's just really interesting.
Yeah, no, it is really interesting because if we imagine how big our galaxy is, then all these 14 galaxies fit in something which is about 4 times as big as the size of just our galaxy.
Wow. So that's, when they say pile up, cluster, like that's seriously dense collection of galaxies.
Yeah, indeed. And it's really, really far away, which is a really nice thing to think about when we think about how the universe has evolved over time. Because when we look at something very, very far away, it means that we're getting that light from very, very long ago. So in this case, we're looking at 12 billion years ago that this pileup happened.
All right, so 12 billion years. Now, correct me if I'm wrong, the universe itself is just under 14 billion years old, right? It's about 13.8 billion years. We go back to the Big Bang, we're pretty sure. So this is only less than 2 billion years after the universe came into existence that we're seeing these things.
And herein lies the problem. Basically, this pileup of galaxies has happened too quickly and gotten too big too quickly.
So hang on, what do you mean? It's gotten too big and it's happened too quickly because that's just not enough time, according to how we understand the universe. That's not enough time for it to actually have happened.
Yeah, so we're going to have to think about our models and think about how we can actually tweak those models to make this new piece of data fit.
It's weird, isn't it? Because 2 billion years on any other time scale, 2 billion years is a really, 1.8 billion years, really long time. Like that's a ludicrous amount of time on most scales. Except when you're talking about the evolution of the universe. And then suddenly it's, no, that's not nearly enough time for these things to form. You astronomers are weird.
Yeah, well, think about what you've got to have happen in that space of time.
All right, what does have to happen in that space of time? What's happened in that 1.8 billion years to give us this stupidly large pile-up of galaxies?
Well, you've had to gone from something, well, essentially nothing, the beginning of the universe where we didn't have anything, no galaxies, no stars, no going down, no atoms.
Well, when you say we didn't have anything, there was massive, roiling, energetic froth is what we had, expanding very rapidly. But we didn't have anything in terms of structure.
No. We didn't even have electrons and protons and neutrons, the building blocks of the rest of the universe. So you've got to go through the evolutionary processes that make all of those constituent parts. And that process takes time.
Not only do you have to get the elementary building blocks, but we're now talking about structure on a grand scale. These are galaxies clustered together, but those galaxies themselves have structure. And within that structure, there are individual stars, all of those things having to evolve and, come into form in a very short space of time.
Yeah. And if you looked at a picture of what these galaxies might look like, then they wouldn't look so dissimilar to the kinds of things we see in the universe around us today.
So does that just mean that we just don't get it? That the models have been wrong to date? I mean, that must be, I was about to say that must be pretty frustrating. No, that must be really exciting for astronomers.
Yeah, I mean, we don't have to throw everything out.
No.
We just have to make some tweaks.
It's not like we don't get anything.
And we just have to adjust actually how fast we think some of these processes can happen.
How do you go about the process of trying to figure out how a universe evolves? I mean, we've come across this question before, on this podcast already. We've only got one universe. So this is an experiment that we're watching in real time. You can't do a whole bunch of universes in the real world and see how they evolve. We can only infer what we can see. But I'm guessing we can simulate these things.
Yeah. And actually, we have to go back and look at what are all the structures that we currently see. I mean, it's amazing to me to think that just over 100 years ago, we didn't know about such things as galaxies.
I know. I mean, isn't that incredible? That within a couple of lifespans, within a couple of generations, we've gone from, we've got a whole bunch of stars in the sky, but we're not really sure what's going on there, to we live in a galaxy which is one of countless galaxies throughout an enormous universe with even larger structures like clusters and filaments and so on. In 100 years.
Yeah, absolutely amazing.
It's not surprising that we'd get something a little bit wrong every once in a while. And have to adjust it. Okay, fair enough. So you were just saying we've got all these different structures that we need to understand.
So let's break that down a little bit into what are the big structures that we can actually see in the universe around us. So we've got galaxies. We're fairly familiar. We've seen some really nice pictures of what our galaxy might look like from the outside.
And we've got a pretty good idea of actually what it will look like as well, because it's not just a guess. There's been the recent, is it the Gaia, the research from the Gaia probe, which has mapped out enormous numbers of stars in our own galaxy, huge numbers, and we've got a really precise idea of what the Milky Way galaxy will look like, even though we're inside it.
Yeah, and we found some other examples that look pretty similar. So the Whirlpool galaxy is one that probably looks quite similar to the Milky Way. And so we've got something on the order of 200, maybe 300 billion stars in our galaxy. There's some other bits as well, but the stars are kind of the key constituents. And if we talk about the size of that galaxy, it's something like 100 light years across.
Right, so 100 light years in diameter.
Yeah.
Okay.
Yeah. And then it turns out that galaxies are not often on their own, while maybe half of all galaxies are in bigger structures. So we have groups and clusters, and those are sort of collections of galaxies. We might have anything up to 100 galaxies in a group, maybe 100 to 1,000 galaxies in a cluster.
Wow, that many.
Yeah.
That many, because I knew that the Milky Way it's got a couple of things going around it. We've got the Magellanic Clouds, which are they considered to be part of the Milky Way, or are they separate?
They're separate galaxies at the moment.
Okay.
They may not well be for all time. We're slowly eating them up. But so our local group, which is very uncreatively named, of galaxies.
Again, well done, astronomers. Yep.
Has something like 30 galaxies in it, which include these little tiny dwarf galaxies like the Large and Small Magellanic Clouds, up to Andromeda, which is another big spiral galaxy like ourselves.
And it is big. I mean, I keep coming back to this, but folks, if you haven't seen a size comparison of the Andromeda galaxy in the night sky, I'll put a link to a good picture and an article about it in the show notes, because it's staggering. It's like, several times the diameter of the moon across in the night sky. We can't see it with the naked eye, or not terribly well at all, but it's huge. This thing is not that far away.
And that's the interesting thing about the scales that you get. So all of these 30 galaxies or so are only in a space of about 3 million light years.
Only 3 million light years. But hang on, let's go back. You said that the Milky Way itself was 100?
100,000.
100,000 light years across. And now we're into the millions of light years. What did you just say? How many light
3
years?
million light years.
3 million light years within, is the size of our local cluster of galaxies.
Yeah.
Okay.
Yeah. So I think what's really interesting is I've got a good analogy actually that I quite like. We do this scale models quite often. So you might have seen a scale model of the solar system, and you see the enormous distances between planets, and you know that the stars are enormously far apart as well. An example I like to use is if you have the sun, as being the size of an orange, how far away is our closest star?
Okay, so the sun is an orange. So I'm going to guess it's like miles away. Like I've got an orange. I'm looking out the window here of your office, Emily, and I'm just thinking it's got to be a lot of miles away.
It's going to be about 2,000 kilometers away.
Wow. Okay. Yeah, I was within a couple of orders of magnitude, 2,000 kilometers away.
So you basically have to go back to Australia.
Okay, and that's just to the nearest star. Okay, so on that scale, how big is our galaxy?
So, well, if we took our galaxy and made that the size of an orange.
Okay, so I've now got a galaxy in my orange.
Well, how far away do you think Andromeda is now?
Couple of kilometers? I don't know. How far away is it?
It's only 2 meters away.
Okay, you're messing with me now. All right, so now I'm looking across your office, and it's basically where your phone is. So that's okay. Well, that makes sense because it's so big in the night sky that it's kind of just got to be just over there.
Yeah. So individual stars and galaxies are really, really far apart, and then you don't get many interactions between individual stars. But galaxies, and especially in groups, are actually pretty close, and they interact all the time.
That kind of makes sense. I mean, even though the distances on our scales are really big, if you look at them in terms of how big the individual objects are and how far apart they are, they're actually relatively close. And that's kind of how gravity works.
Yeah. And how it's interesting then to think about the structures in the universe on all these weird and wonderful different scales. So in our cluster, in our local group, we've got these 30-odd galaxies, and they're not terribly far apart, really. We can zoom out, if you like, again. We can go into superclusters.
Excellent. So galaxies, clusters, superclusters.
Yeah, okay. Not so creatively named again.
Yeah, but, you know.
We are part of a supercluster of galaxies called the Virgo supercluster. There's something like 50,000 galaxies in this supercluster. So we've gone from something maybe 30 galaxies in our local group to tens of thousands in superclusters.
And the supercluster is being defined, again, I'm assuming in terms of gravitational influence, that you know, our cluster are the galaxies which are gravitationally bound.
Yeah.
So what defines the supercluster?
It's the same thing. So basically, like you can have planets going around a sun, which is then going around the galaxy. We can have a local group of galaxies sort of going around the same central point, which is then that whole group is going around something in this enormous supercluster. So it's just kind of different scales going further and further out.
Do you reach a point where you've got, you know, mega uber superclusters, or does it kind of, at the supercluster level, does it kind of pitch off at that point and say, look, these things are effectively independent, or does it just keep going up and up and up?
Well, a bit of both, really. I mean, you can superclusters are pretty loosely defined. You can get up to something like 1 billion light years across, which is getting pretty huge.
That's big, yes, by anyone's scale.
And so by that point, where does the supercluster end and where does the next kind of structure begin is a bit vague. But what we see when we do really, really large surveys of where all the galaxies are is that these kind of superclusters form bigger structures that aren't called clusters anymore. They call them filaments. So they seem to be like these long, thin sort of tentacles, if you like, that are then connected to nodes. I mean, you look at these pictures and it almost reminds you of how neurons work in the brain. It's a similar kind of mapping structure.
And the scale of these things is extraordinary. I mean, we have to remind ourselves and our listeners that we've gone from stars and galaxies. We're now onto clusters of galaxies, superclusters of galaxies. These filaments are enormous. You know, these huge chains of the matter throughout the universe.
They stretch across the entire sky, everywhere we can see.
Unbelievable. And where have those come from? I mean, where does that structure at those biggest scales, where's that come from?
Well, we have to ask ourselves the question of how did the structure in our universe form? Did it form what we call bottom up, meaning we had lots of small things that came together and grew bigger and bigger and bigger? Or did we have some kind of enormous structure that then collapsed down into things that were then smaller and smaller and smaller?
Right. Okay, so you could have had the situation where a bunch of stars, for example, a bunch of stars gathered together and formed a galaxy, and a bunch of galaxies gathered together and formed a group and a cluster and a supercluster, and it's forming, as you say, bottom up. Or it could have been that the largest scale started first, and then things are kind of condensing down out of that, down to finer and finer scales. Is that what you mean?
Yeah. So we've talked about how a star is formed out of basically a big clump of gas. It's kind of taking that idea and extending it all the way out to the size of our whole universe.
Right. So which one is it? Is it bottom up? Is it top down? Is it a bit of both?
Wow, there's a spoiler alert maybe here. We've done a lot of observations and we've done a lot of modelling and simulations as well. And we understand now that it's actually top up. Top up? Bottom up. Oh dear.
You start at the bottom and you work up.
Yeah. So the smaller things formed first. And they're not small. They're not individual stars, but kind of very small clusters that we see in our galaxy today, things called globular clusters.
Right. And then those are gravitationally influencing over vast distances and pulling into these much larger shapes, the superclusters and the filaments and so on, across the universe. That's kind of condensing down to form these.
So you start with a small cluster of maybe a few 100,000 stars, then you pull a few of those together, you start to get a galaxy forming, you pull a few of those together, you get a cluster, you pull a few of those together, you get superclusters.
So how does all of this then come back to the paper that we started with, which is this discovery of this galactic pileup, 12 billion light years away? You said way back at the beginning, 20 minutes ago, that this has all happened too soon, and it's too soon, and it's too much.
Yeah. So when we think about how that structure must have formed, we know how long roughly it takes the first stars to have enough matter to turn on, to start fusion and start glowing. We know sort of quite a lot about the very, very early universe going back from that point. How did the first atoms form? When did the first light emerge from the universe after the Big Bang? And going the other way, we know reasonably well what the dynamics must be to try and pull these structures together. And if you then calculate, well, how long is it going to take to get a galactic pileup of 14 galaxies like this, it ends up being nearly twice as long as the time that it's taken for this particular structure to form.
So the theories, the models say that it should have been something like 4 billion years. And this was only 2 billion after the Big Bang.
Yeah.
It's really interesting that there's this kind of grey area in between, because when you go right back to sort of the very early epochs of the universe after the Big Bang, it's basically particle physics and, grand cosmology. You've got really big but very difficult to test ideas working forward from t equals 0, the very beginning, and trying to figure out what the universe might look like. And then we can make observations of the universe and kind of work backwards towards the Big Bang and say, well, how long would it take stars to turn on and cluster together into galaxies and so on. And we've now found with this discovery that there's this kind of grey area in the middle where coming one way from the Big Bang and the other way from our looking back through time and space, that we need to make these match up. And we've got a couple of billion years worth of discrepancy there to account for, which is kind of fun.
Yeah. So what we've got to do is then, how do we fill in the blank? Well, we start off with making some theoretical predictions and some enormous computer simulations. Because if you want to understand how the largest things in the universe formed, you're going to have some pretty powerful computers to do all the calculations that are necessary to do that.
Which, if you're a bit of a computer nerd astronomer, is going to be great fun.
Oh, yes, yeah.
Because you get to work on some of the biggest, most powerful supercomputers on the planet to simulate entire universes. I mean, what's not fun about that?
Yeah, and so about 20 years ago, we started on these enormous grand simulations of how structure formed in the universe. And one of the older of these simulations, and one of the more famous ones, was called the Millennium Run. And this took a supercomputer, so one of the fastest computers in the world, more than a month to chew through how would you form on the order of 20 million galaxies.
Wow. Mind you, if it wasn't long after the millennium, there's probably an app for our phone that could do the same thing now.
Well, of course, we're continually improving, and the runs that we run today are much, much more sophisticated and have more particles and more interesting physics involved. But let's just take this as an example, because there's some really nice, this is one of the big structure videos that you can go and still see on YouTube. And basically, we put in all the physics that we knew. We knew roughly what the starting point was. We had some physics to tell it what to do, and we had an ending point, which was the observations that we see today. And it was incredibly successful at going from A to B, from the start of what we knew to the end.
And this is a model which is predicting those very large scale structures, isn't it? That it's taking enormous numbers of galaxies and saying, so how do they cluster and evolve over time? And it was incredibly successful. And the pictures are gorgeous.
Yes, yeah, they're lovely. And so you can fly through the larger scale structures in these videos.
If you've never seen
amazing.
that, we'll put a link in the show notes. It's brilliant. It's so much fun.
And this helped us with all sorts of really interesting theories, not just cosmology, because we had to put in things like parameters for dark matter, which without dark matter, you just can't form stuff fast enough, basically. So we learned a huge amount from these kind of simulations. So now we're getting some more observational evidence, which is starting to challenge that. And we're going to have to come either, do two things, I think, simultaneously. We're going to have to get some more data. Because one data point does not a very good science argument make. We need to find some more. And we also need to go and think about what do we need to tweak, say, in those models in order to get at least some of those structures forming faster than they originally did.
Right. I mean, as you said earlier, it's not like we have to throw everything out. You know, there's a lot of the models, which is vast majority of the models are right and accurate and doing the right things. But working out which bits, say, okay, well, what assumptions did we make there? Well, that needs tweaking. What if we did that? Is it likely that we're going to learn something quite new about the evolution of the universe from this?
Well, potentially. I mean, we think that these kind of structures are still quite rare. At maximum, there might be, a dozen other ones.
And sorry, you're talking about the structures?
These enormous ones, yeah.
The galactic pileups.
Exactly.
Right.
These enormous galactic pileups. They're probably not very common. I mean, we would have found more by now, for example, and we would see more evidence of them in the universe around us today, which we don't. So we know that there's a limit to how often they can possibly occur. But just because it's rare doesn't mean it's not interesting. And actually, it might contain a whole set of new physics or slightly tweaks to physics that we already know that we need to consider.
So once again, we just got to go and find some more data.
Yeah. I mean, well, the exciting thing is, first of all, that we know 14 galaxies are in this pileup. There may be as many as 30.
So what, a bunch of them that we just can't see? Or?
Well, there's sort of vaguely some hints of them being there, but we just need some better and more precise observations of the area around this structure to try and pin those other ones down and see if they're part of the same group, basically. So that's step one. Yeah. We need to then find some other ones, maybe, that are like this. This particular result came from a blind survey, so where they took something like a 16th of the sky. And
what do you mean by blind survey?
So they just picked up the data randomly from a particular area and said, well, what's interesting in this?
Right, so it wasn't
segment?
targeted.
Yeah.
It wasn't, we need to look at this thing here. It was, what's interesting here? What can we see? Look at that.
So that kind of tells us something about the statistics of these things. If there's only one in about a 16th of the sky, there's not going to be huge numbers all over the place. But that being said, there's another 15 16ths, if you like, of the sky to go hunting for these things. So obviously having one or two at least more of these structures would be really informative and build better constraints and parameters on the models as well.
So this galactic pileup, we're not seeing it now is kind of interesting. We're seeing it 12 billion years ago because it's 12 billion light years away. It's taken 12 billion years for that light to get to us. So are the galaxies that we're seeing in this cluster, are they normal galaxies that we see around us now? Are they the same as the galaxy that we're in or at Andromeda or other similar ones?
They're a little bit different, actually, and this could tell us something, again, about the formation history as well. So the very first galaxies in the universe were these quite violent galaxies, and there's a particular type that we called starburst galaxies.
Starburst, well, because there's lots of stars bursting out of them. Why are they called starburst galaxies?
Yeah, it was kind of that way, actually. There's lots of stars being formed. So these galaxies, some of them about the same size as the Milky Way, they're forming about 1,000 stars per year.
Okay, I mean, that sounds like a lot, but then again, galaxies are really big. So for comparison, how many would be formed in the Milky Way a year?
maybe one.
Oh, okay, right. So it's 1,000 times more than our galaxy.
Yeah.
Okay, so that's pretty energetic.
And that makes them quite different in their dynamics as well, because if you're forming lots of new stars, then you've got lots of other processes like big supernovae happening. You've got lots of disruption and movement within the galaxy as well.
So there's a lot going on in these galaxies, and that differentiates them from ones that we see around us closer in time and space now.
Yeah. But then what we think is probably what happened to this pile-up, if you like, is that those original 14 galaxies or so would have then attracted more and more galaxies, and it would have grown into one of these super structures, possibly one of the largest things in the universe today.
That's staggering that a little smudge on a picture, almost picked at random, could reveal what is quite possibly the largest structure we've ever observed in the universe.
Yeah, and that we don't actually see around us today.
How random is that?
It's amazing. It's a really, really cool structure.
And that's all we've got time for in this episode of Syzygy. If you've enjoyed what you've heard today, then we'd really like to hear from you. You can contact us at our website, syzygy.fm. That's syzygy.fm. And go and find the form and send us through your comments. If you've got any questions, we'd love to hear those as well. You can contact us on Twitter as well, can't they, Emily?
Yes, at SyzygyPod. Then you can ask your questions, or you can catch up on all the updates and see when the next episode is coming out as well.
Do you know what else would be really cool? Is if you've enjoyed listening to the show, then go on to iTunes or your podcast directory of choice and leave us a review. These things actually matter, because anytime a review gets put on, assuming it's a good review, which it ought to be, then we go up through the charts and other people can find us and other people can share in the absolute awesomeness of the universe, which is ultimately what this is all about, isn't it? But otherwise, that's pretty much all we've got for today. So join us again next time for another episode of Syzygy. But until then, see you later.
Goodbye.
And that's all we've got time for in this... Now I'm getting to the word. This episode of Syzygy.
Just yell it at me.
Come on!
Yeah, I think I made a bit of a faux pas. I'm just checking that.
Oh, really?
I think I got an out by an order of magnitude, but it's also Australia.